3.2 is a technically relevant section, but not worth spending a whole bunch of time on in my opinion. It's about Rolle's theorem and the mean value theorem. So I'll spend maybe 20 minutes on this and then we'll move on. But these theorems are used later in the book to prove super great things. So I'm going to tell you what they are, but you'll probably never see a question on a test specifically geared toward these things just because they're more theoretical and harder to make questions up for. But I'll tell you what they say. They're cool. At least, I don't know, some people probably find it cool. So Rolle's theorem. So suppose f is differentiable on some interval, AB, open interval, and continuous on the closed interval, AB. And the endpoints are equal. So f of a is equal to f of b. Then I can find a c, there exists some number c, value c, in the interval ab, such that f prime of c equals. So this probably means nothing to you. Maybe it means something. But it'll mean a lot more with a picture. So what this is saying, you have a function. It's very nice. It's continuous. It's differentiable. In fact, it's continuous on the closed interval. Maybe I'll talk about what that means in a second. So you have this function that's differentiable and continuous on this interval. So let me draw the interval. Here's A, here's B. And you know that f of A equals f of B. So whatever I do, f of A and f of B have to be at the same height. They have to be equal. What this guy is saying is no matter how you get from this point to this point, you're going to have a derivative equal to 0 at some point. So for example, if you decide for your function to start going up over here, eventually you're going to have to come down to get back to this point. And as soon as you decide to come back down, you have a horizontal tangent line, which means you've made f prime equal to 0. Okay, so that means there's a c value, x equals c, where the derivative equals 0. That's all. That's all it says. Right? If you have a function that starts and stops at the same height, then it must have had a horizontal tangent line somewhere along the way. As long as the function's continuous and different. If it's not continuous, then you can just have a vertical asymptote or something, and you just have a hole at the top here. Does that make sense? Cool. So then, that's Rolle's theorem. I'll give you an example. I'll do an example in a second. But while I have this up here, or while this is fresh in our head, let me give you the mean value theorem. The mean value theorem is exactly the same thing, except you tilt your head a little bit, and then you get the mean value theorem. You're right. You have a function, right? Just like before, same setup. Let f be continuous and differentiable function. Suppose f is differentiable on AB. Continuous on AB. Then there exists a C on the open interval AB such that f prime of C is equal to the slope of the secant line between A and B. This is your picture for Rolle's theorem. Right, the idea for Rolle's theorem is if you start and stop at the same height, then you're going to have a horizontal tangent line somewhere in between. The mean value theorem says nothing about where you start and stop. You can start and stop anywhere you want, right? So here's the interval. Maybe I start up here and I stop down here. Then whatever happens in between, maybe I decide to go down first this time. Come back up here. What the mean value theorem says is that the derivative at some x value is going to be equal to the slope of the secant line. All right, so if you look at this line between the 2 points, between the 2 endpoints, and you calculate the slope of this line, it'll be f of b minus f of a over b minus a. And what this is guaranteeing is that somewhere along here you must have reached a slope of the tangent line, right? You must have had a tangent line that has an equal slope. So m f prime of c here. And if you pick the right c value, these lines will be parallel to the slopes of these. It's just Rolle's theorem tilted. They're technical theorems that help with proofs later, but spend a lot of time on it. So let me do an example of each, and then move on. By the way, why do you think why do you think it has to be continuous on the closed interval? How would you not be continuous on a closed interval? You guys remember, first of all, differentiability is a stronger condition than continuity. If a function is differentiable, it must be continuous. Okay? So the fact that the function is differentiable on the open interval AB means it's already continuous. This extra thing says you can't break off at the endpoints. So thinking of a function like this continuity on AB says I can't do this. Or I just have a function that goes up and then jumps down. Because if I had this kind of function, it would never, this guy never has a horizontal tangent line, right? He never has a zero slope. There's no matching zero slope for the tangent line. So in order for this theorem, the mean value theorem and Rolle's theorem to work, you have to have the function continuous at the endpoint. It has to get back to those endpoints. Anyway, let me do some. Here's a function. my first question. Does f prime of x equal 0 on the open interval 0, 1? So I gave you a function f of x equals x to the fourth minus x cubed. I'm asking you, can I somehow infer that my function's derivative equals 0 on this interval 0 to 1? So Rolle's theorem says if you have the same y values at the endpoints of an interval, then you have to have a zero derivative sometime.
Yes.
So over here, at the endpoints of these intervals at 0 and 1, what does f evaluate to? What's f of 0? 0, and what's f of 1? 0. So because these guys are the same, at some point in between here, you have to have a horizontal tangent. So does f prime of x equal 0 on 0, 1? Yes. F prime of x will be 0 on 0, 1. Fine. Great. Whatever. We love it. It's excellent. So let's find it. Right? Find the value of c. Find c in the interval 0, 1 such that f prime of c equals 0. So where does it happen? If I know it happens, if the theorem tells me it happens, hopefully I can find where it happens. So how would I find the correct c value? It's derivative. I have a function. I have a physical function. So if I want to know where the derivative equals 0, take the derivative. So what's f prime of x? 4x cubed minus 3x squared. But I want to know the c values that make f prime equal to 0. So let me set this equal to 0. So when is 4x cubed minus 3x squared equal to 0? How do we solve this? We can factor out an x squared, leaving us with 4x minus 3. So either x equals 0 or x equals 3/4. So find the c value in 0, 1 so that the derivative is 0. C should equal 3/4. So I knew these endpoints were the same, which told me the derivative has to be 0 somewhere in between 0 and 1. And then I actually calculated it to check. Yeah, 3/4 is between 0 and 1.